Curiosity touched down on Mars in August 2012. It's an epic-making mission. The goal is to delve into the unknown world beneath the surface for signs of past habitability. A diamond-tipped drill on a robotic arm does the delving. Samples of rock and soil obtained in this way are analyzed on the spot. Scientists are looking for organic compounds that might have permitted life on Mars.
Curiosity and the entry, descent, and landing system are revolutionary. It's a real laboratory, and it's a laboratory on wheels. And what that means is we can take it around to different places and study the rocks, and then from that reconstruct different environments that existed in the early history of Mars.
However, Curiosity has been afflicted with a host of problems, from computer glitches to solar interference with communications.
We may have lost the rover forever.
But Curiosity surmounted such crises and resumed its quest. It soon discovered, beneath the famously red Martian terrain, an unexpected world of gray. This finding greatly increased the chance that life has indeed been possible on Mars. Curiosity is continuing its rambles on Mars. This program tracks its adventures over the course of 1 year. Curiosity first entered the Martian atmosphere in August 2012. Executing thousands of commands, it approaches its landing area. One mistake could send it crashing into the surface.
We are in powered flight.
Rover is guided to its target landing area by radar. As it descends, it must skim over a 5,000-meter high mountain range.
Sky crane has started. Safe on Mars.
Curiosity has landed safely on Mars. 2 minutes later,
Images. You got thumbnails. It's the wheel. It's the wheel. We are wheels down on Mars.
the first image received was the brilliant globe of the sun, shining a benediction on Curiosity's mission. Then, far off in the distance, rose the 5,000-meter peak of Mount Sharp.
There was no way to know in advance that the rover would be oriented so that you could see that, but it was it was really great to see the mountain that we had observed from orbit and realize that we could make that target someday.
The rover had landed in a giant crater near Mars's equator. Some scientists speculated that once there was a great body of water here. That made it the perfect place to search for conditions permitting life. Curiosity's adventures were about to begin. The day after the landing, Curiosity raises its head and looks about slowly. It has 2 pairs of navigation cameras. These cameras can cover a 360-degree panorama, taking 3D images of the surrounding terrain. 2 high-resolution cameras are also affixed to the mast for distant and wide shots. The procedure is to take multiple color images, then combine them so as to produce a detailed panorama. From the pebbles in the foreground to the formation several kilometers in the distance, all is revealed in vivid detail. Now that Curiosity's imaging systems have been checked out, it's time to confirm mobility. Mission Control commands the rover to start moving. First off, it goes 4.5 meters directly ahead. Then it executes a 120-degree turn. Next, it will move backward 2.4 meters. Even these baby steps put Mission Control under agonizing pressure. At this time, Mars is about 260 million kilometers from Earth. For each command to reach Curiosity, it takes over 15 minutes. Then for the result to make its way back to Earth, it takes another 15 minutes. In the unlikely event that some mistake is made in a command, it could be fatal to the mission. In the present case, they've waited 3 hours since sending the commands. An image arrives from Curiosity. The rover's tracks on the Martian surface, precisely as commanded. This is a promising start. Curiosity landed at the red dot in the plains at the base of Mount Sharp. The rover's first destination lies 500 meters to the east, at the seams of 3 rock plates, comprised of different materials from different eras.
We recognized that we were going to be able to study a kind of a rock that we saw from orbit that had this signature of very high thermal inertia. And we thought maybe the water was involved in precipitating minerals that filled in the pore space. That's why we decided to go, because we thought maybe the property of thermal inertia has something to do with water.
Curiosity fixes its navigation cameras on its destination. Mars, the red planet, glows in the night sky. It is Earth's neighbor. Could it harbor life? People have long pondered that question. One of them, in the late 19th century, was the American astronomer Percival Lowell. His observations of the planet over 15 years led him to conclude that there were traces of numerous canal-like structures on the Martian surface. Lowell concluded that, unquestionably, Mars, too, boasted an advanced civilization. But in the 20th century, Mars missions sent back images showing no trace of actual canals. What the images did show, however, looked like traces of the flow of water. Even if there was no intelligent life, might there not be at least some primitive organisms? Speculation mounted. What are the requirements for life to exist? On Earth, there are a minimum of 3. First, liquid water. Among its many and varied functions, it conveys nourishment to every part of our bodies. Second, an energy source. This is vital for such basic aspects of life as growth and reproduction. Third, organic compounds. These are the raw materials out of which life takes shape. In 1997, however, the Pathfinder probe made a stunning discovery that seemed to dash hopes of life on Mars. With expertise in both geology and biology, Jack Farmer has been a valued contributor to every major Mars mission from Pathfinder onwards.
I suggested that we go to the outflow channel called Ares Vallis, which was draining from this terrain of potentially lots of different kinds of habitable environments, carrying water from the subsurface up, draining out and depositing right where we landed.
However, when the surfaces of the rocks and ground were inspected directly, scientists were disappointed. The rust-colored Martian terrain looked extremely inhospitable. Jack Farmer calls such a highly oxidized surface a real killer for life.
Oxidation reactions are always going on the surface of Mars, and this kind of surface skin of basaltic materials like this gets turned to something like this. So Mars is red, for a good reason, I guess.
This is how it happens. Cosmic rays pass right through the thin Martian atmosphere, directly striking the planet's surface. That produces a large number of active oxygen atoms. They bind with iron in the rock, producing the characteristic rust color of oxidation. Active oxygen has a powerful impact on organic compounds, the very building blocks of life. It splits them off, disintegrating the compounds.
If they're there, they're very shortly oxidized and turned into CO2.
The bleak, reddish surface of Mars. It proclaims the fierce oxidation of a sterile world. Hopes faded for even a historically habitable Mars. But now, Jack Farmer and other scientists are following a promising new lead. They're looking inside rock formations, where cosmic rays cannot reach.
If you go in the subsurface, different story. If you can get down deep enough where there could be water present, then you've got a whole different ballgame, and I think you could open the door for life down there.
Could there be, hidden beneath the arid terrain of Mars, an entirely different environment, one hospitable to life? Answering that grand question is Curiosity's mission. Pre-op checklist completed. Curiosity is good to go. As if to pray for an indefinite continuation of its mission, Curiosity etches the infinity symbol in the Martian soil. August 27th, about 3 weeks since the landing. Curiosity is ready to venture forth. One of its early finds is a strangely shaped rock. This pyramid-shaped rock, about 30 centimeters on an edge. It makes a good test subject for some new equipment. The ChemCam, a laser spectrometer and imager. As the laser beam bores in, the ChemCam analyzes light from the vaporized rock to determine composition. The pyramid rock is found to be a volcanic rock, basalt, rich in metals like iron and magnesium. Its remarkable angular shape is thought to be the result of wind erosion. Curiosity continues its trek through fantastically bleak scenery. As it travels, its cameras record some incredible sights. Like this partial solar eclipse. Mars has 2 moons. One of them, Phobos, has passed overhead, partially obscuring the sun. This is the first time a Martian solar eclipse has been captured so distinctly. Curiosity soldiers on, sending back image after image, at a pace of more than 200 a day.
I think that's all the high-level notes I wanted to make, other than we did just have...
One image in particular catches the attention of mission scientists back on Earth.
So it looks like we're generally doing a little bit better on the passes.
It was taken just 100 meters from the landing site. It shows a large number of pebbles strewn about at the base of some uplifted bedrock. Very similar terrain can be seen on Earth. Dry riverbeds, These pebbles were rounded by friction as the current ran its course. Now the eroded, dried-up channel is littered with them. Compare them side by side. Similar indeed. This is incontrovertible proof that water used to flow in this region. The first of those 3 requirements for life has already been satisfied. Experts can use the size and disposition of the rocks to guess how that river flowed in ages past on Mars. The river would have been about knee-deep, and it flowed at about the speed of a human walking.
So when we saw the ancient streambed gravel, you think of flowing water. And one of the things that you want to do is go with the flow. Follow that river. See if you can see where it takes you. Because on Earth, when you follow a river, it either leads to an ocean or it leads to a lake.
So curiosity goes with the flow, eastward. What sort of scenery awaits it? Before we follow curiosity any further, let's acquaint ourselves with the hard work done by the mission control staff. This is mission control at JPL. Work here continues regardless of day or night. The main reason for that is the time difference between Earth and Mars. Mars takes longer to rotate on its axis than Earth does, so its day is 40 minutes longer, which means the time difference between Earth and Mars after 3 days is 2 hours. After 6 days, it's 4 hours. The gap widens. Curiosity can be activated only during the Martian daytime, but there are times when that might be in the middle of the night on Earth. One of Curiosity's planners and drivers, John Wright, is starting work at 9 p.m. It's the beginning of a hard day's night. His first step is to review the log of the previous day's itinerary. Next, he analyzes closely the 3D images produced by Curiosity and decides which route to take next.
So with 3D, I can see there's a small mound here. There's a large mound right here. So if I'm going to be driving forward, I'm going to go over that mound and then down a fairly steep hill on the other side. So I might say, maybe that's a little steeper than I would like to drive, but let's try to analyze some other areas. So we might look at other areas. I had to work sometimes all night, sometimes all day, sometimes halfway from the middle of the day to the middle of the night, all different kinds of odd shifts.
Okay, this side.
Well, sometimes I would go, since my wife would be asleep when I would go home, I'd go someplace to a late night restaurant and have dinner. Or breakfast or whatever it was, because it was just easier to do that. But then, after all that work, to find something really interesting and really amazing, it does make it worthwhile. I mean, that's why we're here, is just to do exactly that.
About 2 months after the landing. Just short of its next science destination, Curiosity encounters a new formation. the rock nest drift of windblown sand and dust. Curiosity takes this opportunity to test for organic compounds, which are vital to life and are a key target of the mission. The SAM laboratory suite is highly efficient at detecting organic compounds. Paul Mahaffey is NASA's principal investigator for these analyses on the Curiosity mission.
So this is a full-size model of SAM on Mars. This is the electronics box. This is a mass spectrometer. This is a gas chromatograph. And our third instrument, the tunable laser spectrometer, is down here.
All these analytical instruments are packed into a laboratory suite about the size of a microwave oven. And in fact, samples introduced into it are first heated at high temperatures. The gases given off by this process are then analyzed minutely by the mass spectrometer to determine their constituents. When the sand and dust of the rock nest site were analyzed, the results were stunning. Trace amounts of chloromethane, an organic compound, were detected. At last, a key ingredient for life on Mars had been discovered. The scientific community was all abuzz. However, at a hastily called news conference, the project's leaders were cautious in their claims.
SAM has no definitive detection to report of organic compounds with these first set of experiments.
The SAM laboratory suite had been assembled in a terrestrial clean room. Despite all the team's precautions, could impurities have entered it? Possibly it was those impurities that had been detected.
As far as the first analysis of the rock nest sample is concerned, we certainly couldn't definitively rule out that most or even all of that carbon might be from Earth.
But this uncertainty only intensified the hopes placed on Curiosity. Soon the rover would arrive at its primary science destination, where it would be expected to find definitive proof. December 7th, 2012. After about 4 Earth months, the rover has finally reached its primary destination for exploration. A new type of terrain has come into view. To the southeast, a bulge of bedrock. To the northeast, a low-lying area. Curiosity heads into the low-lying area. What will it find? A basin stretching as far as the eye can see. The bedrock is cracked but flat, like an interminable expanse of stepping stones in some giant garden.
The character of the rock is much different. We have mud cracks and things of that nature that suggest perhaps this was a lake that actually, a shallow lake that would dry out occasionally and produce cracking.
This dried-out lakebed has been named Yellowknife Bay. That ancient river Curiosity discovered right after setting out had once flowed down here and created a magnificent lake. Next, Curiosity will put a drill to work to obtain a historic first sample from underneath the red ground of Mars. The rover descends carefully into the bay itself. It will spend the next 40 days exploring the bay's every nook and cranny.
And then we drove up to another particular part of the outcrop where you could go up it centimeter by centimeter by centimeter and do a detailed study. And then we did that. And then ultimately, that helped us pick the place where we wanted to drill.
The basin was vast. Where to drill was indeed a matter requiring thought and planning. Curiosity finally finds a target that looks perfect for drilling. A flat and stable rock bed. It is given the name John Klein. February 8th, 2013. Whether it's been day or night on Earth, John Wright has continued his skillful maneuvering of the Curiosity rover, and he's been formulating complicated commands to operate the drill. He runs simulation after simulation. Accurately excavating the target spot requires extremely delicate manipulation of Curiosity's robotic arm.
So when you put the arm out, it just sags down because of the weight, and it can sag up to 7 or 8 centimeters below where you command it to. When you say go to 10 centimeters, it says, well, in this configuration, I might have 5 centimeters of droop, so I'll command it to 15 and expect it to droop down to 10. That, making sure all that worked right, was the stressful part.
After spending more than 5 hours assembling the command sequences, Wright sends them to Curiosity. The next day brings images of the results.
That's an image here of our first hole on Mars. Big success. Yep. Woo! Yeah.
This was the first time in history that human beings had drilled a hole into another planet. Note the color. Beneath the red surface, gray rock tinged with green.
I think when we first saw the color of the rock that was being exposed as a result of drilling was one of the most exciting moments of the entire mission to me. It was right up there with landing itself, because when you see this gray color and you know the chemistry in advance, when the iron is more in the reduced state, you can get a grayer color, which is the color of, say, for example, iron metal is gray because all the iron is reduced in that state.
The sample extracted from the rock is placed into SAM, the specialized onboard laboratory. There it's analyzed for the presence of organic compounds. But just when Mission Control thought the data was coming in fine,
It'll be hard to see above the noise floor in the FFTs given how weak the low gain signal is.
An unforeseen circumstance. The main computer controlling all of Curiosity's equipment has developed a serious glitch. The data stream has suddenly been suspended. The mission specialists concentrate as a group on troubleshooting the problem. They pinpoint the culprit, the main computer's flash memory, dedicated to preserving Curiosity's analytical data. What's worse, further analysis reveals that after several hours, if nothing is done, Curiosity will cease receiving instructions from Earth.
This computer would stop talking to Earth. We wouldn't be able to send commands to it. It would stop. It would do no more help for us, and the computer would forever be locked in this perpetual loop, never communicating to us again. We may have lost the rover forever.
If communication with Curiosity becomes impossible, the rover will be stranded on Mars as a pile of very expensive junk. Is there no way to prevent that worst-case scenario? Their discussions produce, in the end, an all-or-nothing solution.
We've got to do something. We've got to kill this computer. It's not going to kill itself. This computer is going crazy. We have to take it offline.
So the troublesome primary or A-side computer will be taken offline, and they'll switch to the B-side backup. The problem is, once they've shut down the main computer, will the backup boot up properly or not? There are absolutely no guarantees. But there are also no alternatives. So the main computer is shut down, and the backup is switched on. The result?
But we waited and waited. When the minute came, 5, 4, 3, 2, 1. Nothing. We saw no signal. We all look at each other. Did we do the math wrong? Let's go check the math. No, we didn't do the math wrong. Now we're very nervous that maybe we messed this whole process up and that we missed the command or did something wrong.
Project staff all resign themselves to the worst.
We confirm we are within the FFT display. We don't see any signal coming.
Happy. 3 minutes later, doop, there is a signal. Later on, we realized that the new computer watch hadn't been updated. Okay, so that makes sense, but we didn't realize it was off by 3 minutes. But we were very relieved. Once we saw that signal, knew we were in good shape.
Curiosity had surmounted the crisis and obtained some hard-won samples of gray Martian rock. The precious analytical data were successfully streamed to Earth. Washington, D.C. NASA held a press conference at its national headquarters. Project leaders reported on Curiosity's latest achievements and on the possibility of past life on Mars.
Yellowknife Bay. This was an ancient environment with the right elements, minerals indicating a near neutral environment, and slightly salty liquid water. All the prerequisites to support life. A habitable environment.
The first step was to introduce the gray powder obtained by the drill into the Chemin instrument, a component analyzer. Analysis confirmed that the deeper the sample, the weaker the oxidation of the rock. This finding meant that the second requirement for life on Mars, an energy source, had now been satisfied.
It's a battery. And basically, these minerals that Dave and Paul were telling you about, they're effectively like batteries. Some of them are negatively charged, and they have various oxidation states.
The difference in oxidation states meant that electrons could flow from areas of weaker oxidation to areas of stronger oxidation. Even the minute flow of these electrons constitutes energy and could promote an environment conducive to the nurture of microorganisms. Jack Farmer points out that similar environments occur on Earth. This is a sample from inside a cave, in a place that sunlight does not reach. But check it out under a microscope. And masses of a stringy microorganism are still living in the sample.
It always participates in the oxidation of reduced iron in systems like that. So it's mining this reduced iron spring for its energy. It's not using sunlight, because there's no sunlight there. It's using only chemistry, redox chemistry.
Curiosity had proved that even under the surface of Mars, an energy source existed sufficient to satisfy one of the three requirements for life.
We're no longer just looking at a red, rusty Mars. We have evidence that there's something going on in the shallow subsurface. So you don't have to go very far, right? A few centimeters, and you're into a totally different world.
And made a model.
Next, there was the question of whether the rock samples contained the final requirement for life on Mars: organic compounds. Concerned about potential contamination from Earth, the Mars team had given Curiosity's onboard analytical equipment a blank run to establish baselines. Only then did they introduce the sample for analysis. The result? Another finding of chloromethane. It was nearly 5 times the amount detected during the blank run. Clearly, most of what was detected in the sample had not been brought along inadvertently from Earth. But Paul Mahaffey, in charge of the analysis, knew they could not jump to any conclusions. Chloromethane alone is insufficient to guarantee the presence of life.
Chloromethane compounds are the simplest class of organic compounds that you can find. It's very much on the simple end of the types of complexity that we're looking for.
Curiosity will have to locate more complex organics. Undaunted, the rover heads off to its next science objective. However, it will first undergo an ordeal even more harrowing than the last. Up to this point in the mission, Curiosity has faithfully executed every command sent to it. But ever since that glitch developed with the main computer, Curiosity has been run by its B-side or backup computer. If this backup computer develops any serious trouble, that really will be the end for this groundbreaking mission.
We also need to figure out what happened to the A side and figure out whether or not we can restore it so that we can use it again if we need to in the future.
A new problem is looming at this crucial moment: solar interference with the mission's communications signals. With an orbital period almost double Earth's, Mars finds itself, once every 2 years, on the opposite side of the Sun from Earth. In other words, the Sun is interposed between Earth and Mars, blocking a direct line of communication. The Sun emits an exceptional amount of charged particles. They stream off the Sun as the solar wind. When signals are sent from Mars to Earth, the solar wind can interfere, letting only some of the data arrive. What's even scarier is that commands sent to Curiosity could be corrupted en route, delivering the wrong instructions. So for about a month, communications with Curiosity will be deliberately shut down. Project engineers are desperate to get the main computer back online before Curiosity goes into standby mode.
So, I need to we can set the pointing angles to right and down.
The computer repair work continues day and night.
And we did it all in about 3.5 weeks, and just in time for conjunction. So it was a very exciting month of March.
Succeeding in their repairs before the conjunction of the Earth, Sun, and Mars, the team is able to safely ride out this period of suspended communications. After 1 month, Curiosity is back online, communicating with Earth. Engineers immediately send commands for a second drilling experiment. And again, Grey Mars appears. But analysis once again finds only chloromethane, no complex organics. Does this mean there are in fact no complex organics at all on Mars? At this point, one scientist offered a new proposition concerning the possibility of past life on Mars. Chris McKay is a co-investigator on the Curiosity mission. McKay has an explanation for why complex organic compounds have not been found on Mars. A clue, he says, is provided by the large amount of perchlorate found on Mars. What does he mean? McKay demonstrates with an informal experiment.
Okay, put in a little perchlorate. And a little sugar. The sugar represents the organics on Mars that we would like to detect.
Sugar, the well-known complex organic compound resulting from photosynthesis by the sugarcane plant.
As I heat it,
Sam detects organics in the same way, by heating the sample. McKay is mimicking the basic process. The sugar begins to melt.
Sugar's active.
That activates the perchlorate. A moment later,
The chlorate's going to heat up. That's the perchlorate burning.
So the activated perchlorate destroys complex organic compounds like sugar. The reaction also produces chloromethane.
Right. Once you heat up the sample with organics, it's all going to get turned into chlorinated organic compounds like chloromethane. Even if there was a biosignature in the sample, say some cells, they would be destroyed by the perchlorate.
But that means that in a location with less perchlorate, there would be a better chance of finding complex organics. And McKay has a theory about just where to look: deeper underground.
That material certainly had organics when it was deposited. So something is bleaching the organics out. And that something must be perchlorate chemistry activated by radiation. So we have to go deeper.
Curiosity's drill can go 10 centimeters deep at most. But the side of a cliff might provide a way to get at exposed rock from deeper layers. A place like Mount Sharp, seen in that snapshot taken just after landing.
We go up Mount Sharp and we find a place where a landslide or an impact has removed material, and we can get down below the ground more than 5 meters with the rover. That would be wonderful.
Day 299 since the landing. Its investigation of Yellowknife Bay complete. Curiosity has a new destination. It's heading off to Mount Sharp. There, complex organic compounds, those building blocks of life, may yet await discovery.
Maybe we can find an environment where there's not so much perchlorate. Or maybe we can find an environment that just has lesser amounts of oxidants. That's what we're trying to do. We're trying to figure out how to unlock the code for the preservation of organics now.
As a geobiologist, Jack Farmer greatly looks forward to this next chapter of Curiosity's saga.
When you combine geology with the quest for life, it's a whole other ballgame, and that's really what's kept me interested. Being able to see through that story in the rocks, to ask the question, could life have survived here in the past? Could it still be there today in the subsurface?
It's only been 1 year so far, and Curiosity has already shown us a brand new Grey Mars. Its next destination on Mars is a land whose colors and contours we still do not know. Curiosity is exploring new territory in the effort to determine whether or not Mars has ever been able to sustain life. That epic quest continues.